Hi everybody, we're Team Bill and this is our final design review. So the problem we want to solve is that current methods of selling food and beverages at large outdoor events such as stadiums or music festivals are very inefficient. Customers, they don't want to get up and leave their seat and leave the product that they came and paid their money to come see, and they don't want to miss out on the event. As well, owners of the venue, they want to maximize the amount of revenue they can bring in off sales of concessions, including food and drinks. And there's a company called Oracle, which actually did a lot of research on this exact problem. And they found that customers would be a lot more likely to spend money if they don't have to wait in line and they don't have to miss out on the event. So current solutions to the problem only go halfway. They have apps like SeatServe, which you order on the app on your phone in game, but then you still need a runner to come bring the food directly to you. So we want to develop a solution that eliminates the middleman and fully solves the problem. We want to autonomously deliver the food either to a client or to a middleman near the client to where the client does not have to walk far and miss out on what they came to see. So the project definition, in order to solve the problem, we need to design a mechanism on the drone that would be able to pick up and drop off packages containing food or beverages to a location close to where the customers who ordered it are located. And we also need an algorithm that would drive the drones to follow paths to take them from where the food is picked up to where it needs to be dropped off. And we also need a method for the drones to find the correct spot to land so they know where to pick up and drop off the package. So when we started, we came up with three different solutions for the problem. The first being that we wanted to design a drone that would lower the food directly down to the customer. The second solution being a drone that would deliver food to a drop-off location near the customer that's manned by some staff. And the third being a drone that delivers food to a runner who's further away, and that runner would then deliver food to the client. So in the PDR, initially, we wanted to go with solution one, but we determined that we couldn't fully trust people in those cases. We didn't want to risk people who might have some other agenda grabbing hold of the drone and injuring themselves or breaking the drone. So we chose to go with solution two. We felt that it was the safest method because not only do we not need to fly directly over people, it minimizes the amount of interactions that customers will have with the drones. So the scope of the project, initially we had a scope and we redefined it right before the CDR due to the fact that integration in Weebots with the flight controller and the model of the drone wasn't plausible in our time frame. So the final scope is that ECE needs to develop a code that enables a simulated drone to autonomously pick up a food delivery box from a marked point, navigate through a static environment with obstacles, and drop off the food delivery box within 2 feet of another marked point, and then navigate back to the pickup location. And the mechanical side, we need thoroughly detailed and analyzed CAD models of all the components of the system, including the drone body, a box to hold the food, and a mechanism for the box to be attached and detached to the drone autonomously. So to go about showing this, because we couldn't integrate everything to Weebots, we chose to do isolated physical simulations of the image recognition system and the box pickup mechanism, as well as an integrated Python simulation in which we would combine the flight controller, the state estimator, and the path planner, and demonstrate the performance of each subsystem in those three simulations. And also we needed a list of hardware and technical drawings to show how to physically build the drone and how we would plan to fit the hardware together, as well as a wiring diagram to show how to wire all the electrical components needed for the system. So we did want to reiterate that there are several points that we want to specifically state are outside of our scope. We're not going to worry about code that would control the physical drone because there's already open source code out there that's ready to be loaded straight onto the Raspberry Pi we're going to use that would control the drone. We also want to avoid mechanisms to avoid moving obstacles like other drones. The drones aren't going to talk to each other and know where each other are at. And we are not going to consider a dynamic environment for the path planner or the flight controller. And we're also not going to design a ground station that's giving orders to the drone or design an app to where customers would input their order and no type of customer interface.
System design. For our drone model, we designed the Mehta 600 Pro to use as the base of our product. It's a hexacopter, so it is more reliable than a quadcopter, and it can handle loads of up to 15 pounds. As seen in the table below, the GM Mehta 600 Pro is the cheapest drone that carries more than 15 pounds. The model has been taken from the DJI website and modified to accommodate our payload attachment system. The landing gear was removed in order to make space for the payload attachment system, and we have modeled our own landing gear. The propeller models were also not included in the provided drone model, so simplified propellers were modeled to fill in the space. In order to ensure that the bottom plate of the drone could withstand the weight of our payload, SolidWorks FVA was run in week 3 to show that there was no von Mises forces over the yield strength under a load of 15 pounds. So all of the work in Weebots was done before we decided to not use Weebots in modeling our drone, but in order to understand how the model would work in Weebots, a simplified drone model was created and imported. Using propeller nodes, we can specify the axes of each individual propeller as well as their thrust directions. The propeller node includes several functions. You can change the orientation of the propeller axes, as well as the positions of the center of thrust. The device is just a rotation motor that you can specify the speed and torque on. Fast helix nodes are solid nodes that define the cylinder that propellers spin in. Slow helix nodes are solid nodes that define the actual propeller. In order to determine thrust constants, the below equation is used, where you input the thrust and get T1 and T2, which are the thrust constants. The full assembly was created once we finished designing all of the components and found models for the necessary electronics. We also found that the Arduino couldn't be mounted on the mounting plate and had to be mounted onto the top of the drone. After the full assembly was finished, the full assembly was imported into Weebots as solid nodes, and the bounding boxes were tweaked to fit the drone better. However, since we weren't using Weebots to analyze our drone anymore, this is as far as we went with Weebots. Because we weren't using Weebots anymore, we decided to model the pickup mechanism in SolidWorks. To the right, you can see the drone landing and picking up the box.
So to analyze the payload attachment system, we ran an FVA with the entire system attached to the chassis of the drone. A 5-pound weight, which is our maximum payload, was placed inside the box to simulate the drone carrying a payload. And we excluded the entire drone from the analysis due to the size of the file containing the drone model. If we put it in, the file size would be too large and the simulation would not run in sufficient time. So only the chassis was included because that's the part of the drone where we're attaching the entire mechanism to. So we ran the FVA for two different orientations, one with the gravity vector pointing downwards to simulate the drone hovering, and another with the gravity vector tilted at 25 degrees so that we can simulate when the drone begins to turn at an angle so that it can travel horizontally in the air. We want to make sure that the system would be stable during that scenario as well. We also ran a motion study in which the system was accelerated to 3 Gs in each direction, the X, the Y, and the Z direction, as well as we wanted to test for torques experienced during angular accelerations. So we chose 300 degrees per second squared for the pitch angle and an angular acceleration of 150 degrees per second squared for the yaw angle. And we ran this motion study and then imported the loads experienced on the system into FVA analyses for each individual component. And then we added constraints where we needed to simulate rolling contact where faces of the parts come into contact with each other, and fixed geometry where there would be screws in so that the part would not be able to move at that location. And here shown is the clamping arms as well as the box, which are 2 major components. And we found that everything was able to hold up under the dynamic loads, so our entire system will be stable during flight.
For our delivery box, the design began with the choice of material, starting with polypropylene, as the material is currently used to make boxes for food delivery. This was compared to materials such as PE copolymer and homopolymer. These materials were available in SolidWorks and like others researched, but their strength was not ideal for the small amount of material we would use. The original design was the top-facing lid. This was changed to front-facing lid to allow for easier access for the contents inside the box. Originally, the box needed to be shelled to save weight, as the original weight was too heavy to fly on board the drone. The shell was originally made with 0.1 inch in thickness and later changed to 0.15 inches. The original weight without a shell was 13.4 pounds, and the new weight with the shell was 4.1 pounds. The next design was rounded using fillets to avoid sharp edges in the most areas possible. The lid was improved by adding a rubber bang and changing the latch system for less heat leakage through the sides. The lid and box were joined first, then the attachment plates to allow for easier changes in individual models. The total weight of the box assembly with attachment plates was 7 pounds. After receiving feedback from our peers in the CDR presentation, we finalized our product to appear like that shown on the right. The shells were removed, the hollow inside had been replaced with a thin wall of 0.13 of PP copolymer, the same material we had previously used. Analysis will be shown in the later section, and the final weight of the box was 4.2 pounds, a further improvement. The box was assembled alongside the payload attachment system using hardware found in the McMaster-Carr website, which is listed in our report. For a simulation listed further in the presentation, we used virtual bolts and pins to simulate the same function. These virtual connections were used as to save the computing power compared to the CAD models, which increased our simulation times. The landing gear. We created a landing gear assembly that would be able to support the drone, payload attachment system, and a max load of 5 pounds. We also made sure that the box laid at least 1 inch above the ground to avoid collisions on impact. The legs are reversible so we can easily replace it, and it is made of nylon, the same material as the base, which it is attached to.
Hello, I will be representing our system dynamics and control and navigation algorithms. So for our hexacopter model that we previously discussed, we first had to model its dynamics. And modeling the dynamics requires us to understand what coordinate system we will be performing. The two main coordinate system in our problem are the inertial coordinate system, which is fixed on the ground, and its z-axis is pointing towards the center of the Earth. The y is the north, and the y is the east, and the x to the north. And the body coordinate, which is fixed to the body of the hexacopter, its z coordinate is pointing towards the perpendicular down to the body, and the x to the front, and the y to the right of the hexacopter. We also have 3 angles of rotation, which are the roll, pitch, and yaw, which each of these angles have their own coordinate systems. And in order to transfer from the body frame to inertial frame and vice versa, we use this matrix, which uses the 3 angles multiplied together to perform that transformation. Then in each of those coordinate systems, we define our state variables. We have 3 translational and 3 rotational variables with their time derivatives, which sum up to 12, total of 12 state variables. The 3 of the rotational are in the body coordinate, and 3 of the transitional are in the inertial coordinate system. We can see that they are derived from derivative of one another, and there were some assumptions such as linearity of the system, which we will not include this matrix transformation here, and our x3 dot, which is the roll, pitch, and yaw derivative, will be equal to our velocity vector in the body frame. And we have the forces of thrust and drag, which drag is due to different aerodynamic forces on the body, and thrust is the vertical forces on the propellers. Later on, once we figure out the dynamic of the system, then we found a controller. Our controller was initially built for a quadcopter system, which uses 4 motors, but then we took that controller, made a block diagram of it to understand it better, and then replaced it in risk kinematics model at the end for a hexacopter. Basically, this controller takes the state variables x, y, z, and their derivatives, and the roll, pitch, yaw, or the theta, phi, and gamma, and their derivatives, and the planner gives the X, Y, Z destinations and the yaw target, which are 4 values we're controlling our drone with. And by doing the math and some coordinate transformation, at the end, it gives the vertical altitude and 3 torques in the roll pitch yaw direction. And later on, these values get converted to the motor values and are given to the our plant, which is the hexacopter. Once we obtain the motor values, those motor values will act on the system and generate the thrust. However, for our inverse kinematics model that I showed, we were required to calculate that those 6 motor values, which was here, using this inverse dynamics equation. We initially found the inverse dynamics equation from this paper, but our model, it wasn't working well on the model because of some simplifications we had already. We kept the thrust signals and the yaw signals as it was in this paper, but then we came up with our roll and pitch signal values represented in this matrix. Here is one result of our control system, our finalized model, which gives the true state of our hexacopter in our simulation. And we gave step responses in each direction in a time interval sequentially. And we obtained their steady state error and overshoot values using these control parameters. The steady state error, as you can see, takes about 3 to 6 seconds, and the values overshoot for about 0.01 to 0.08 meters. Then once we added our estimator, which in actual real case, our drone will read those values, some of these control parameters have changed. Here is another test case, which we give a raising ramp and lowering ramp in X and Y direction, and raising ramp in the Z direction, and 0 to 40 degree in the yaw direction. And here is a portion of this control response of this control signal, which showcases that our hexacopter works fine and stable in our simulation environment. There were other types of control inputs that we gave, which were the randomized one, as I showed before, the step responses, or different type of inputs to make sure our system is stable once we give control signals, control inputs of 1 meter in each X and Y direction, and again 1 meter, and about 45 degrees in the yaw direction. Then, as I said, our system requires a state estimation because it does not have access to its true state. So for our state estimation design, we use 2 main functional blocks, which are the complementary filter and the common filter. So our complementary filter basically works in the body frame or the copter frame that I initially showed, and it uses the IMU values, which are the angular rate and the linear accelerations from the accelerometer. Then the complementary filter gives the roll pitch yaw angles and the accelerations to the common filter, and then common filter uses the GPS to do the corrections or the observation updates, and during landing it also uses the camera to generate the 12 state needed for our controller. Basically, this is the feedback diagram of our general system. Then for our estimation and our sensors, we needed to model our sensors. After some studies, we observed that the sensors of the IMU, who are the gyro, the accelerometer, and the magnetometer, the gyro has a lower variance but high bias because the gyros are inherently operating in a higher bias mode. And also, since we are reading the angles from the gyro, we are constantly integrating the angular velocities, and that causes the accumulation of the error. However, the accelerations read the angle directly by using the direction of the gravity. And then, but since we have some um, jittery movement in the acceleration axis, our acceleration has higher deviation. Then we found their standard deviation value from their data sheet by calculating that using this formula, which I obtained from the TI's Precision Lab, which uses a noise density and bandwidth, and chose the lowest possible standard deviation values just for simplicity. Also, both the sensors are operating in low noise mode. And for GPS and the altimeter, we are using the Six Sigma method, which in the GPS specs, we have 2.5 meter accuracy. And for the altimeter, we have 10 centimeter accuracy, which resulted to this standard deviations. In the Kalman filter, basically, once the values are filtered in the complementary filter, the Roland, pitch, and yaw will be fed into the time update block. The time update basically takes the accelerations and predicts the position of the hexacopter. And once a observation is done using the GPS or the camera, that gets corrected. We see the time rate of each of the sensors, which we also included. We found from the data sheets from the GPS, and for the IMU, we actually put the time rate of the calculations as well, because it takes time to calculate these values. Then at the end, we have the 6 states in the inertial frame, which Kalman filter was supposed to do. And we already have the other 6 in the body frame from the complementary filter. Here is a result for that ramp input that I showed. We see that if our system works within few meters of its initial position, we have a deviation of less than 0.5 meters in the X, Y, and Z, and we have about less than a degree deviation in our roll and pitch angles. And here is a result of the path that we did. The path planner was already generated. This path had already generated this path within this environment, and our drone moves. One thing we realized is that the combination of the system works fine, except on the corners, which there are some overshoots happening, and we tried to also solve that issue. And this is the error analysis of that path that I showed. We actually noticed that on larger scales, because our control inputs are a little bit further from each other, it also affects our estimation analysis, our estimation results, and we get an error about something between 1.5 to 2 meters in X and Y, and less values in Z because we're using the altimeter, and less than 2 degrees or like 1 degrees in the roll and pitch. And lastly, we also were concerned about any vibrational movements, because we see lots of vibration in the actual state of our system, and we wanted to do a vibrational analysis, make sure if it doesn't cross. And as the mechanical system reported, the vibrations are the lowest vibration was 28 hertz, which we clearly see that this avoids that frequency. And then at the end, they did our simulation in Rose Bowl environment, and we got portion of the path done, traversed by our system, which marks a little success for our work. So we had some overshoots, but that was something that we constantly worked on fixing.
So for the path planner portion of our design, we initially, in the first few weeks, decided to use Dijkstra's algorithm because it was simple to implement. We did this by manually drawing a graph over the venue, picking out specific points that represented concession stands and delivery points, and various intermediary points for transit. However, the downsides of this approach became apparent pretty quickly. It was a very tedious process to create one graph, and even though it was very low resolution. You see on the right the graph we made. And it took about probably 45 minutes to an hour to create this one. And there's probably, I think, only 17 points here. And then the following weeks, we decided to use A star instead in a totally new way to represent the venue. A star is also a smarter version of Dijkstra's algorithm. It uses a heuristic to search in the direction of where the goal will be, whereas Dijkstra searches blindly in all directions. And then we represented the data instead of by manually creating a graph. We represented the venue as an image seen in the middle, as a color-coded image, where each color means a different thing. Here, black is like a wide open space the drone can fly freely, and then the blue represents areas where there's some sort of obstacle that the drone must fly over. In this case, it's the side of the stadium, or it's trees that the drone has to fly over. Transparent areas are out of bounds zones. We don't want the drones to fly way outside the stadium or fly into the side of a building or something. So that's where we do that. And then the green areas are areas where we want to discourage the drone from flying, but it's still allowed to. Those are high cost areas. They add extra cost to the heuristic. So we want the drone to fly along the outside of the stadium as much as possible, avoid people. And then the inside of the stadium is colored green because we want the drone to just cut into the stadium at the very last minute to minimize the interaction with the drone and people because there are safety concerns there. However, there are still problems with this, even though it was a little better. There was a higher resolution of the representation of the venue. Mainly it stuck to edges of the venue, stuck to the out of bounds zones, and it also produced sharp 90-degree turns. So this wasn't optimal because the drone in real life is going to vary a little bit. So you see on the left is the yellow path is the calculated path in just a test example venue. On the right, the pink/purple path is the path the drone actually took. So you see there's variation there. If it's right on the edge of the path, we'll obviously go out of bounds, accidentally fly over people when we shouldn't. So more work became necessary. So in the final iteration, we added something called cost diffusion. Basically, we added a green bubble around all the transparent and out of bounds areas, and also a slight gradient along the high cost areas, as well as just the plain green zones. This has the effect of keeping, it's like a buffer zone to keep the drone away from right up against the edge. And then we also did a post-processing to smooth out the path a little bit. We put it through a low pass filter so the small jagged little edges disappeared. And also we changed the heuristic for A star so that it would, along with calculating the cost of the total route, it would also encourage straightness in the path. And then next, we see that the path planner now works well in multiple venues. We tested over 70 different paths, and it works well enough to avoid flying over people and keeping the drone in bounds. Here's a wiring diagram of the whole system. We based this off another paper we found for a drone with a nut that also landed with a camera recognition system. The motors, like electronic speed controller, power distribution board, and batteries all come with the drone. They're already pre-wired with a DJI drone that we're basing our design off of. Then there's also the Pixie Hawk 4 flight controller and power module that integrate together, and then that controls the actual movement of the drone. The Raspberry Pi and camera control the last final landing sequence. The Raspberry Pi camera obviously detects the tag or captures the video feed. The Raspberry Pi detects the tag, calculates the relative position, and sends that data to the flight controller. And GPS and the altimeter simply act as sensors. And then there's an IMU built into the flight controller as well. And then we also, with all these electronic components set out, we calculated the total power budget. There's a big difference between loaded and unloaded flight. We found that unloaded flight could be up to 37 minutes, and loaded flight was around 20 minutes. And we calculated this just for hovering because we didn't know at what speed the drone would fly. So because of that, and because we set 20 minutes as the low end. And also we found that the total battery capacity was 780 watt hours. So all these small little components like the Raspberry Pi and the GPS and altimeter would make very little difference and would not drain the battery much compared to the motors. The motors are the vast majority of the power draw.
When we evaluated our sensors for the drone, we noticed that the GPS was only accurate within a few meters, which wouldn't be accurate enough for our landing and docking procedures. So we decided that we would go with an image recognition option instead for landing. And the two options that we were looking at were April Tag and Aruko. April Tag has more configuration options and a better range, but Aruko is more fit for our technical stack, so we decided to use that one instead. We found an Aruko package with calibration and estimation scripts, which we modified for our own use. And the calibration script receives input images and outputs the intrinsic camera values that are unique to each camera. And the estimation script returns an estimated position and an attitude with respect to the camera and with respect to the position. We found that the calibration script wasn't very reliable and the output units were scaled incorrectly, so we decided to make our own entirely. And we did this by hard coding several images that we took from different positions and orientations from the camera. And although this is something that we wouldn't want to do if we were like repeating the process, we decided that it would be okay for this situation because we'd be using the same camera on each of the drones and we'd only have to repeat it a few times. Additionally, we couldn't test this reliably in a physical camera, so we had to run automated tests in Weebots. So after establishing a proof of concept with the physical camera, we began implementing the calibration and estimation scripts in Weebots. The calibration script images were taken at several orientations and locations and outputted the following camera matrix and distortion vector, which are the intrinsic camera values that are unique to the specific camera from which the images came from. And you could see at the bottom here, we have a total error of 3%. Since we evaluated this across different images, some of them evaluated at different values, and 3% is a pretty good margin for what we were trying to obtain. So after the calibration script, we implemented the estimation algorithm in Weebots. Once we did this, we verified its accuracy by comparing the actual position in the Weebots world to the estimated position that the algorithm outputted. And in this image here, you could see an example where the estimated camera position is -173, and the physical position that we set in Weebots is also -173. But more on that later as we show the actual analytical values across several different experiments. We also only decided to get a position output since our other sensors would be able to take care of the orientation sensing, which was already reliable enough for docking. After this, we obtained output results for different types of camera movements. We obtained several different outputs for movements in just the X, Y, and Z directions, as well as stepped increments in each direction across multiple tests. And here's an example of some of the results. Right here, we're looking at X, Y, and Z values separately. Something that we've noticed is that the error actually increases the further the distance is away. So after obtaining those results, we decided to graph the error as a function of distance and see how those were related together. And in this graph, you could see at higher distances, the error becomes more and more increased. And around 10 meters, the error becomes 1 meter, which is beyond our margin of accuracy that we're trying to get. So we determined that our image recognition would only work out to 10 meters for our application. So after all of these results, we determined that this sensor doesn't operate like our other sensors, and that the error increases as the distance from the tag increases. So this sensor mechanism will only work out to 10 meters, whereas our other ones work throughout the entire flight of the drone. And we also evaluated some other issues that could occur. One of them is that the size of our Aruko tag is very large. It's 1.5 meters long, which is about the same length as the drone. And so if the drone is any closer than 2 meters, it won't be able to detect the image since it'll be wider than the camera view. So there's a couple implementations for this. What we decided to do was once it's above 2 meters, it will just start descending slowly and ignore the image recognition code. If that ends up being an issue in the real world, then what another option we could do is have 2 Aruko tags, one large one and one small one, so that they could both be detected from a large distance, but as it gets closer, the small one will be used for docking. And another issue that we aren't exactly able to test in Weebots is glare and inconsistent lighting and shading issues, which could very well cause problems in the real world.
So to analyze the payload attachment system, we ran an FVA with the entire system attached to the chassis of the drone. A 5-pound weight, which is our maximum payload, was placed inside the box to simulate the drone carrying a payload. And we excluded the entire drone from the analysis due to the size of the file containing the drone model. If we put it in, the file size would be too large and the simulation would not run in sufficient time. So only the chassis was included because that's the part of the drone where we're attaching the entire mechanism to. So we ran the FVA for two different orientations, one with the gravity vector pointing downwards to simulate the drone hovering, and another with the gravity vector tilted at 25 degrees so that we can simulate when the drone begins to turn at an angle so that it can travel horizontally in the air. We want to make sure that the system would be stable during that scenario as well. We also ran a motion study in which the system was accelerated to 3 Gs in each direction, the X, the Y, and the Z direction, as well as we wanted to test for torques experienced during angular accelerations. So we chose 300 degrees per second squared for the pitch angle and an angular acceleration of 150 degrees per second squared for the yaw angle. And we ran this motion study and then imported the loads experienced on the system into FVA analyses for each individual component. And then we added constraints where we needed to simulate rolling contact where faces of the parts come into contact with each other, and fixed geometry where there would be screws in so that the part would not be able to move at that location. And here shown is the clamping arms as well as the box, which are 2 major components. And we found that everything was able to hold up under the dynamic loads. So our entire system will be stable during flight.
The first FVA we ran was applied to the bottom of the original box as a 5 psi load. This simulated the maximum weight we would allow in our box as simulating hot dogs and large drinks. The bottom of the box was fixed and FVA was run. To the right we see the displacement chart. The displacement shows a maximum displacement of 0.8 millimeters below the center of the base. We can also see some slight displacement along the walls, but these are minimal. The test showed that the shelling of our material did not cause significant displacement in our box system. The box was then put through a thermal test with an internal temperature of 160 degrees Fahrenheit, simulating food safe temperatures, with the outside being 80 degrees Fahrenheit, simulating a warm day. After the simulating, the FVA, small leakage was shown at the joint hinges, but besides that, no major leakage of heat was shown in our materials, proving that this box can maintain food safe temperatures for at least 10 minutes. The first test performed with a system attached to the box was a load analysis using a 5-pound downward force, as this simulated the maximum payload. The material of the top plate was cut out in parts where we did not experience much stress. The test was rerun, and we can see the results to the right. This test showed us where we could save on weight for our attachment plate, in addition to showing it can support up to 5 pounds. After the CDR and constructing the final box, we conducted FVA analysis to ensure the box was able to hold a maximum load of 5 pounds. To the right, we see the stress and displacement plots. Compared to the previous versions, we see a decrease in displacement and stress, which means that this version will be able to support these items better than the previous box. This meets our desired outcome. Modal analysis was used to see how the system would react under different frequencies, such as those produced by our flight controller, so we could avoid or mitigate these frequencies. From this analysis, we saw the first mode was 5 Hz. This was mostly in the box with slight movement, which was not of much concern to us. The second shows a mode at 10 Hz, which was also moving the box slightly, also of no concern to us. At 10 Hz, we see some distortion in the base itself, but some improvements to the base height and box thickness. The first significant mode was improved to 26 Hz. This analysis showed us where to add support and increase thickness in our models. The landing gear analysis. The landing gear was subject to a downward force representing the full 35 pounds of a possible max load scenario. This would simulate the drone, payload attachment system, box, and maximum payload. The plots on the right show that our stresses experienced by the parts are below the yield strength. In addition, the deflection of the landing gear is most 21 millimeters, which is below the radial length of our base leg. This signifies that it will be able to support our drone and is a successful design.
When it comes to the performance of the Pathfinder, overall it worked okay. It fulfilled the major requirements, but we found that it was not very robust or portable. And what I mean by not very portable is that there's many different parameters that have to be set by hand that sometimes need to be changed from venue to venue in order to get a good path, the path you want. For example, for the diffusion feature, there's the number of iterations that the image gets blurred, the kernel size for the actual blurring, the value of the green pixel that transparent pixels are replaced with. There's also the relative weight of the green pixels compared to just normal distance. All those things can change it. We see in these images on the left, the diffusion parameters were a little different. So there's a little more green cloud on the edges compared to the right. And also the cell relative weight of the green pixels, or the cell weight, is less on the left than on the right. So it actually takes that shortcut on that green bridge rather than on the right where it goes all the way around. And so it's hard to make one set of parameters that works for all types of venues, and sometimes it needs to be changed by hand. And then also we found that sometimes it produces suboptimal paths. We see on the middle and left image. On the bottom, the drone or the path planner produces a path that kind of has to go back on itself. It goes up and to the left until the y coordinate matches with the target, but then it runs into a high cost area where will be a lot of people. You can see on the Coachella map specifically, there's just a lot of cars and campsites there. So it's forced to go south along the road that it should have followed the whole way before it goes back to the path. And you see on the roads, despite the post-processing done to try and smooth out the path, there's still some jagged edges in there. However, despite these flaws, we still think that the performance of the Pathfinder is adequate. The major requirements were, it finds a path from A to B, it stays in bounds, it doesn't fly off to anywhere it wants, and it avoids people as much as possible. You see on the left, this was actually the map that created on demo day by Peter. He tried to break the Pathfinder as much as possible by creating a maze of transparent walls, which indicate the out of bounds zones, and the Pathfinder successfully navigated through the maze and made it all the way to the endpoint without going out of bounds. And on the right, even though in the last slide we saw that the drone kind of likes to fly straight towards the goal without looking ahead to see if there's obstacles, we see on the right, the drone successfully stays outside of the stadium as much as possible, goes the long way around all the way until it's really close to its final destination. Then it cuts in to that point and spends minimal time in the stadium. So we think those major requirements have been fulfilled there.